Yeah, first, thanks for the invitation. It's a great honor and also a difficult task to provide an introduction for algorithmic information theory, because probably there are at least some people know things much better than me, and so still I was asked to provide some general introduction. So I'll try to do something, and we'll see how it works. So you know what this first things in all courses on information theory is just we try to consider this trivial example. So if we know that an alphabet has 4 letters, and then we need 2 bits per letter, but if we know that the frequencies are different, then we find a better code, just like frequent letters should have, so if we have, I don't know, if we have 1/8, yeah, we need A, B, C, and D, and in this way we can economize and get, for a letter, for probability pi, we have log over 1 over pi bits, and it's for frequency, it's not probability, just one string. So the average numbers of bits per letter is this entropy, and of course it's all true if pi is at power of 2, but still we can, then we need rounding if it doesn't help. But so the start of Kolmogorov's idea was that in this way we use statistical regularities, but there are many types of them, not only frequencies. For example, there are frequencies of pairs or something like this. And also there are some regularities which are not of statistic nature. So if like any computable function like pi is very gives a sequence which is highly compressible, because it's a finite program, can produce as many bits as we want. So the idea was to start kind of information theory which takes into account all the regularities, not only statistical ones. And this was the goal of Kolmogorov. And so statistical theory defines information in random variables, and algorithmic theory should define the information in finite objects like, I don't know, graphs or sequences of bits or sequences of letters or images or whatever. And then there is a very simple idea, just now amount of information in an object. It's how many bits we needed to describe it. So it's a compressed size of the object. But there is a classical thing which I think is called Berry paradox. That if you just use the words in a sense of a natural language, then they of course are not consistent. We are getting immediately to a paradox. So we have an integer. So not only finitely many integer can be defined by 1,000 English words. So there is a minimal one which cannot, and still is defined by this sentence, which definitely has less than 1,000 words. So this is a paradox which shows that we should be very careful, like in Gödel theorem, with the truth, and here we should be careful with what is definition. But still we can try a more formal way. We just say that definition is a program. So we just look at the minimal length of a program which produces a given object. And so this is kind of a formal definition. Of course, we can say it's like compressed size. The program itself is a compressed version of the object. And so we can think about this as, of course, it depends on the choice of language. So this is not invariant yet. But still, it's a start for theory. And I think that for a long time, why it was discovered so late, why it only in the middle of 60s it was considered. I think that the people think that this is so trivial that nothing interesting can be obtained out of this. So of course, we can give a definition. So we can define it's not definition, just a word. We can consider any partial computer function as a programming language or decompressor or something like this. So if it's programming language, then the language is without input. A program is run, X is run, and then the interpreter for a programming language, V, produces some string, and then X is a program for the Z, and also X is a compressed version of Z, and so on. So it's just a wording. And then we can define the complexity in a trivial, as I said, the minimal length of a program which produces a given string Z. So it's so simple that hard to believe that something reasonable can come out of it.
Is this the same as saying that you have a Turing machine? Because, I mean, so the definition that I usually see is that there's a Turing machine, you're writing down the description of a Turing machine.
So you mean that the Turing, so I don't really understand. So you think just V is a Turing machine. So there is a description, there is a Turing machine, and the machine is applied to the description.
X is the Turing machine, and V
as the output of this machine.
V is the output of this machine. But with Turing machines, there are some machines that don't output anything, that don't halt. You know?
Yeah, and it's not only in Turing machines, every time there are machines that don't halt.
But in your definition, there are...
No, V is also partial. V is an interpreter of language. So, no, for Turing machines, the problem is not that they don't hold, but the problem is that it's not clear how to count the size of them. So the Turing machine has states and has alphabet, so we need to make some combination of all this to get to measure in some reasonable units. And Turing machines are probably not completely optimal in this. If we make a description of a Turing machine and measure the size of this description, it's most probably, it depends on the choice of specific model, but at least for some Turing machine, it's not the optimal way to, we get something too large. If we measure a minimal size of the Turing machine, which prints on the tape the strings Z and stops.
So here when you write partial, you mean that it's on some inputs it's not defined?
Yeah. So it's V. You can think that V is kind of just an interpreter of a language, some programming language, and we put the description of this language, a description in this language, and then get. So, but formally, it's just a kind of length of length of minimal element in the pre-image of Z under some V. So, just to see that this is very simple and almost trivial, let's imagine that we do not require V to be computable. So, imagine that V can be arbitrary function. So, this description, the mapping from descriptions to strings or for programs to outputs can be just arbitrary function. Then, of course, it's clear which complexity function we can obtain in this way. We just the only property is that there is only at most 2 to the k strings of complexity k, because they each should have descriptions of size k. So we have somehow we have strings here that needs descriptions, and we have one string of description of length 0, 2 descriptions of length 1, 4 descriptions of length 2, and V maps something this to some string, so there are at most 1 string of complexity 0, maybe two other strings of complexity 1, and 4 strings of complexity 2, and so on. At most 4 strings. And of course, if we have any objects in these quantities, then we can assign arbitrarily the descriptions and claim that for this function we have these complexities. So this is a completely stupid idea to classify consider just the sets of size at most 1, at most 2, at most 4. What can we obtain in this way? But still, if we require So this is necessary and sufficient condition for the complexity function. And also, of course, if we want just in advance, we have some string z, and we want this string to be simple, it's achieved trivially. We just map consider v, which maps empty string to z, and then the z is complexity 0. So it looks like a very strange theory, and still there is some observation which can be made even in this stupid model without a requirement of computability. So imagine we have two decompressors, v0 and v1, alternative. And so that they have two functions, the complexity functions. And we want to construct one decompressor which beats both in terms it provides as efficient as at least as both. So we want this function CV be smaller both than CV0 and CV1. But we have to, of course, it's not possible without some. So sorry? Oh, yeah, it should be 1, yeah. So you can guess what you should do for this. So you just put like this. So first bit, so the program for V is just first bit says 0 and 1, which V0 or V1 we should use, and then the rest is read as a program for this. So we just use one bit for selecting the decompressor, and then just another bit for the rest for things. And then, of course, if it also works for computable things, if just V0 and V1 are computable, then this one is also computable. So if we need to prove find some application for everything, one can say that the standard format for compressed files like zip format it does like this. There are some, actually it's indeed the case. They start with some header which explains which decompression algorithm they should use. So but of course they spend not 1 bit, but I think 16 or 32 bits for this header, but still not bits by bytes actually, but still they use it. Yeah, and then we use the same thing for sequence of bits, sequence infinitely many. No, actually, if we want to have n decompressor, then we need log n additional bits to specify which one we use. And if we have an infinite sequence, of course, we can decide that we can construct some v which starts with a self-delimited description of I. So, for example, we need it to be self-delimited in the sense that it's clear when it stops. So if we just put a binary representation of I, this is bad because we do not know whether we should stop reading it at some point. But you can do it like put 0, 0, 1, 1, just double each bit, and then put block of different bits for as a termination signal or whatever. So this overhead is O of log I. So we need some overhead, and then we can beat all the VI, but with the constant which depends on I. So it will formally it will be 2 log I plus C if we use this thing. So and this shows that we can use it for computable things. So we can enumerate all the interpreter for all the possible languages, including very stupid one, but all computable functions and then then get something which beats up to a constant, beats every computable thing. And this trivial observation is called Kolmogorov-Solomonov Theorem. Actually, it has very strange history. There was a paper in, I think, beginning of 60s written by Ray Solomonov, a very nice guy from Boston. And it's a paper on machine learning, and it was is information and control, but it was not a mathematical paper. So there are funny sentences like, so if the definition, Solomonov writes that if a definition number this and this is not consistent, then we should modify it in some way, keeping more attention to the properties of theorem this and this, then the theorem that and that. So it's not a mathematical paper, but there is some footnote which more or less contains this theorem. Yeah.
Why the log I is considered small? Because I can be huge, right? I mean, the best I might be something.
Yeah. No. Of course, I can be huge, but no, actually, what we do, we start. No, I is the length of the code for the language. So of course, if we take a huge modern programming language, which like C++++,
Even otherwise, when you
yeah,
say there's an optimal computable decompressor, the proof
yeah,
will presumably go by saying, okay, suppose it's a decompressor, then it will occur somewhere in the
yeah.
sequence. But that point might be, there's no bound on where that point is.
There is no bound. No.
How do you say it's optimal?
No. Optimality is defined that for every other one there exists a constant such that the first one is bounded by the first complexity is bounded by the second plus this constant.
Yeah, so I guess I'm complaining about what is a constant and what's not a constant.
The index could be the description itself, right?
Yeah.
I mean,
yeah.
So that's the log of I, right? So you at most double the cost.
Oh, I see. So
if you arrange them, the index of the V's depends on
just on the description.
Itself.
Okay.
Then you can do it with a constant. That's the meaning.
So I see that I'm mixing things. So there is a pre-ordering on decompressors. We say that V is better, that V prime, if there exists some constant C, such that for every Z, complexity of Z with respect to V is at most complexity of Z respect to V prime plus this constant. So if we have two decompressors, then we say that they are in this, the first is better or almost as good as another one.
Okay.
And the formal claim is there exists a minimal element in this ordering. So you may rightfully complain that what does it mean practically, whether it has some reasonable meaning or whatever, but just formal answer is just constant depends on this. Almost as good already involves a quantifier, existential quantifier over this trade-off constant.
Yeah, so in order to use this, we need a bound on the number of these.
No, here we have no. If we have a bound on number of v's, we can just reserve. If we know that there are n of them, we can reserve log n bits, and then we need the self-delimiting thing. But but here we deal with the infinite sequence, so we allow any computable functions. They can be all enumerated, and so here we have infinitely many v's.
How do you know how much space you need to put?
But this is not a fixed space. This is a self-delimiting code. So we take I, which is a number, then we take a binary representation of I, and we double each beat, for example. So here I is equal to 0, 1, 1, 0. And then we put 0, 1. as a termination sign. So now when our universal or optimal decompressor gets a string, it starts reading the pairs of bits until it sees the different bits. And then it says, oh, I should stop here, and this is without any doubling. This is the input, and this is a number of the decompressor we should simulate. So in this way. Okay, so what people say is just let's fix, they say that let's fix an optimal U somehow, and then call this the Kolmogorov complexity. It's a bit cheating because we don't know which optimal U will fix, so it's not clear whether we can say that the Kolmogorov complexity is really defined. But also, I just want to say that this type of has another application, not in zip, but there were in old times when people were not so afraid of viruses, there was something which is called self-extracting archive. You just get an executable file and you run it, and this executable file actually contains of a small program, and the rest was data. And then the program starts to run on this data and produces the long file. So the self-extracting archive can beat any other archive because if there is some efficient method to compress something, to decompress something, this method can be put in the beginning, and then the rest will be the data for it. Okay, so this is. Yeah, so let me start with some positive things. For example, complexity is bounded by length because we can consider the trivial decompressor, which just does nothing, no compression. This is X. Then for this view, of course, the complexity is just exactly the length. And by the way, I can just to check that we all understand the same things. Let imagine the compressor is like this, 0x. So what is the function CV of z? How it's defined? What it will happen for this specific V? Not always.
Not always,
half of it are infinite, and half of it is length minus 1. So it's infinite if x doesn't start, if z doesn't start with 0, if z is 1 something, and of it's a length minus 1. If z is 0, some 0 w, because just w is mapped to. So this is somehow it's captures the entire idea of what we are able to do or what we are unable to do. When we construct a decompressor, we make some trade-off. We can decide that some things should have good compression, but then for other strings we are forced to use long codes. So and this says that somehow there is a universal balance for this up to a constant. And another theorem. So if we say that the complexity is the amount of information, then one would expect that the information cannot be created by use of algorithms. Conservation of information. So if we have some algorithm A, then normally the complexity of output of this algorithm should be bounded by the complexity of input. Plus, of course, the algorithm can just append some long string, so there should be some constant depending on the algorithm. So for every algorithm, there exists a constant CA, such that for every string, yeah.
Someone call it, it is somehow the opposite of the conservation of information.
So it's
I would say traceability of information or something, right? It's something. So if it acts as information, then it's it has the code. Its code has to have the same
information. Somehow. Yeah, information cannot be contained, obtained from nothing.
Yeah.
There is another law which says that randomness cannot be obtained from nothing.
So
Yeah.
Is that for a different C than the one? Because if you use CV for that, then an A is an algorithm that just put a 0 in front of U, then you get like infinitely smaller than something finite. Does it make sense?
No, this is universal. So. And the proof is just using the universality. Let's denote this universal by U. So we just compare, the proof is just we compare U with U A of U of something. Because what was the description of some object U with this U becomes a description of A of U with this thing. So there is you should somehow be accustomed to this constant which depends on something but not on something else. So it's a bit confusing at first, but so we fix some universal decompressor and fix the complexity, and then we say that we use always the same decompressor here and there. And then we take some algorithm and we say that this algorithm cannot create new information. So if we have applied to some U, then the complexity may decrease at most by some constant which depends on the algorithm but not on, well, maybe U is a bad thing. Let's write it here.
But A has to be recursive. Are you assuming something about A, or can A also be completely non-recursive or anything?
No. A is an algorithm. So now, from now, we start dealing only with partial computable functions, decompressors. Consider the universal one, and A here is also an algorithm. Of course, if A is arbitrary thing, it can just there are strings of arbitrary high complexity. So A can produce a strings of complexity much higher than the whatever.
This is only valid for a universal decompressor, right? You cannot put the UV and into onto.
Yeah, of course for some special one. Yeah, for example, if we have this decompressor which measures length, of course algorithm can increase the length. So the idea is that this complexity is somehow measures everything compressed, so algorithm doesn't change anything.
Sorry, just very basic question.
Yeah.
So what's the difference between an algorithm and a decompressor?
No difference. By decompressor, we allow any computable function, any algorithm. So the only why we use the word decompressor, just as it's a way how we use algorithm in this setting. So we assume we consider any algorithm V, and just okay. So we consider partial computable functions just a function computed by algorithm. So all these are synonyms. Partial compute. Okay, you can make a distinction between an algorithm which has a time complexity and function which it computes. But for now, it's not the difference. So we consider any computable transformations, any functions, any algorithms, any interpreters of all programming languages, but just okay. So what I wanted to say. So there is still something which is even true for non-computable functions, but we use it for computable functions. So there is a, if we want to, we will also noted it here. So if we look, for example, of number of objects of complexity less than 3, then there is at least 7 of them, because there is 1, 2, and 4. So the number of objects of complexity less than n is less than 2 to the n. So it's a kind of calibration of size. So of course, if we multiply complexity by 2 or divide it by 8 and measure it not in bits but in bytes, it's just another measure, but then the calibration is no more valid. So this is just a calibration thing. And of course, there are some objects which are highly compressible. So if we have a long sequence of zeros or digits of pi or whatever, so of course, to produce such a thing, we need only to know n. So there is an algorithmic transformation which gets a binary representation of n and maps it into this string. So complexity still can be very small for long object. There is entire things which is called, we can consider the maximal object of complexity n, at most n, and it's a busy beaver, it's called busy beaver number. But yeah. But still, if some objects are compressible, still most objects are not compressible, because if we consider strings of length n, so we have all strings of length n, and if we consider strings of complexity less than n minus c, so they are compressible more by c bits. And then they form a very small fraction, because the quantity is less than 2 to the n minus c. So the probability to run into such a thing is 1 over 2 to the c. So to have something, to have a random sequence compressible by 100 bits is almost impossible, because it's 2 to the minus 100. Such as things never happen. So if I don't know whether there are some philosophers, or maybe you know some philosophers, but there is questions for them. So there is a kind of law. So I can, if I have more time, I can toss 8,000 coins and get a sequence of 1,000 bytes, then run on this laptop, run the zip program, and I claim that it never will be, after compression, will be less than 900 instead of 10,000. So this is practically we can be practically as sure in this as in any other law of physics, like measurement of I don't know, of gravity or whatever, will also just the same type of guarantees we have here. But so it's a kind of a law of nature.
But I think it cannot.
Sorry? So you get a sequence of thousands bytes, and we claim that the law says that it has compressed length at least 900. At least 900. So the bad event, this is highly compressible. And so I can make bets so it's like the law of nature. But the question is then if it's whether it's a consequence of some other law of nature, or it's independent law of nature, or what. So I think that philosophers could say a lot of this about this. So now I want to say why it's not so good as we can hope. What are the problems with this approach? So first problem was already mentioned, that its complexity is defined only up to a O of 1 additive change. So if we want to ask, for example, no, of course there is an option. You say that this decompressor is that decompressor. So there are many optimal ones, many interpreters of many different languages, and you say that, look, I'd like to, I don't know, for this purpose maybe there was some natural candidates, like there was language called Forth, which was very concise. But anyway, you can declare your favorite language to be the right one and say this is the complexity function. But of course, it's a kind of cheating. So you cannot study questions like this without some specific choice. So there is an entire program of some people try to make this choice, and you can find even a website which you can enter some sequence, and they try to say which of them are simpler or compressible better or whatever. But it's not. It's just a kind of natural. They try some natural ways of compression, but it's not something that can be proved. And also there is another bad thing, that the function is not computable. So even if we agree on some optimal programming language and want to use it for something, we still cannot, because and this has a very nice simple proof. So I think many of you have heard it, but still let me try to explain. So imagine it's computable. So there is an algorithm which tells you the complexity. Then of course you can search for objects of for any number. You can find a string which computed complexity is at least this number. So you can define such string xn here. And if you can compute complexity of every string, you can just search all of them and at least one of them is found. And of course, it should be found because only finitely many strings have small complexity. And then there is a contradiction, because it should have complexity n, but also it can be obtained from n. So we know that if it's obtained from n, and n has complexity, logarithmic complexity, so it's at the same time large and small. So there is a contradiction here. So this is kind of a proof which somehow follows this Berry paradox. If complexity was, then we say that if the notion of definition in Berry paradox was well defined, we got a contradiction. So if the complexity now can be computed, then we get a contradiction. And then there is probably there is a kind of digression. Most famous person in complexity field, most advertised person at least, is Chaitin, and he proved what was his most impressive observation is just he proved a Gödel theorem in a Chaitin way. So Gödel theorem say that not all those true statements are provable, and Chaitin specifies says more specifically which statements are not provable. So even if we want to prove statement that complexity is high, so the statements not about variables, but just the statements of the form I didn't know. And here we fix some fixed optimal decompressor, and then consider statements of this form. They are actually universal statements that say that there is no program of length less than 17 that terminates and gives this. Now, of course, this should be some specific sequence. So even if we are interested not in all truth in the world, but only the strange truth of this form, still there is no way to prove all of them. And we already more or less have seen the proof.
Sorry,
yeah?
I'm not saying something simple. Why cannot the numerator on everything that has 17 less 17?
Yeah, so you can try to apply our decompressor to all things of strings length smaller than 17, and then to check that this is not an output. That's what you say. But of course you try this, but then you start some computations are running and running and running, and that you don't know whether they will never stop, or they will stop and produce something like this.
Because they're assuming that's okay.
yeah. Now, actually, there is also an easy application of a fixed point theorem. I don't know even, it's folklore, I don't know from whom I heard this, that there exists some program, some fixed for each programming language. You can write some program, and for this program, you cannot prove in set theory, for example, that this program is different from something. So for every program Q, there is no proof that P is not equivalent to Q. Actually, such a program should never terminate, because if it terminates, then you can see what it produces, and so it's a lot of things which it does not. But if it's a non-terminating program, it's how can you prove that it's different from some other program? If you run and so this is the simple corollary of cleanly fixed point theorem. If we want to, if it's not the case, then for every program we can find something provably non-equivalent to it, and so we violate cleanly fixed point theorem. So this is somehow the other proof of Chaitin result, but it's digression. Sorry. So what I wanted to say that there are the statements only finitely many m can appear. So for every theory, like set theory or arithmetic, there is a maximal number of complexity which can be proved. Maximal possible provable lower bound for complexity of whatever is things, and the argument is the same. So if it's not the case, so these things can be provable for large m, for arbitrarily large m, then we can just look at all the proofs and wait until we prove that some string has complexity greater than m, and in this way we again computably find a string of complexity, large complexity, and so on. Now, of course, you assume that your theory is not consistent, but all the axioms are true in the standard model, because otherwise this complexity may be only provably exceeding m, but not really exceeding m. And again, we give this the same things. And also, there is a digression. There are interesting questions about the statement of this form as axioms. So some of them, most of them are, almost all of them are not provable. So we can add them as axioms. It's a natural idea. For example, we can toss a coin, get a long sequence, and add as an axiom that it's not compressible much. But you can try to study which of them. They are not all equally powerful. Some of them are statements of this type are almost useless, but other can be have some power in terms of formal theory. But this is another thing I just wanted to say. Okay, so after bad news, we need some good news, and good news that still, if we want to consider things asymptotically, it is quite possible. So for example, if we have a sequence, we can take the initial segments of its infinite sequence. We can try to consider the density of information in it. We can take first n bits, or not even bits, but first n elements, and compute the complexity divided by n, and consider some limit behavior. We can consider lim_inf of this. And this is what is called effective Hausdorff dimension. It was noted only quite recently in 2000 something that this is a very natural notion. So
it's the effective dimension of the sequence.
Its dimension. It's kind of a strange thing. It's the dimension of one sequence. And dimension of a set can be then defined as a maximal dimension of its elements. So it's something very strange, because in classical, in our classical intuition, the dimension of a set measures how many things it has. not how bad elements it has, just how many. But in algorithmic world, it makes sense to consider the dimension of one specific object, and then a dimension of a set defined as a maximal dimension of its elements is very close to classical dimension. So how, if a set is not too bad, its dimension is measured by the maximal complexity of its elements. And then we can prove a theorem which relates formally the entropy and Kolmogorov complexity. So if we take a binary, a biased coin with some probability p and 1 minus p, and take toss this coin and get a sequence x0, x1, and so on, with independent identical distributed sequences, according to coins, according to this distribution, almost with probability 1, we get a sequence of Hausdorff dimension h of p, where it's Shen entropy. So somehow we measure the same amount of information as it does Shannon, but Shannon did it only for probabilistic objects, and now we somehow can deal with finite objects. So it's kind of a generalization of Shannon theory. Actually, okay. And also there is a finite version of this thing. So if we have a finite, not infinitely many coin tossing, but only finitely many, n of them, then we get some string which has some complexity, and this complexity is now a random variable for a random string distributed according to this distribution. Complexity is a random variable. So we can ask what is, for example, the average of this random variable, or what is the so there are here is something different said. If we just, it's not a probability but a frequency, then we can have just a upper bound, not an average. But for average, it's also true. It's complex. It's close to entropy.
Because the maximal entropy distribution, if you only have that information, is going to be precisely, you guess that the frequency is the probability.
Yeah. So the distribution is very close to distribution concentrated on the string with fixed frequency. So it's more or less the. But also for a practical viewpoint, so different people have different favorite programming languages. But at least in old times, programming languages were something not very complicated. I don't know, maybe only few of us, including myself, remember that when there was first popular Pascal compiler for microcomputers, like it was called Turbo Pascal and something like this. I think the computer has only 64 kilobytes, and most of them was occupied by something. So the compiler used like 10 kilobytes, and so actually, if we say that the natural length of programming language, natural complexity of programming language, like thousands or tens of thousands, then if we want to measure the complexity of a long novel or a DNA genome or whatever, still the difference in the choice of programming language is not that important.
So what if you had not IID samples but just an arbitrary sequence? Can you look at
If you have what?
Suppose x1, you have a sequence of random variables, it's arbitrary, but there's some probability distribution.
Yeah.
Can you say that this limit is the same as the limit of the entropy of the joint distribution of x1 through xn divided by n?
No, this is the problem, because so here we have the limit. So if we all the time include new and new variables, then of course each variable is used only once. Each distribution is used only once, so its entropy is not revealed really. So if we just have some for example, independent random variables, xi1, xi, and so on, then complexity, then xi1 is used only once. it's tried only once. So its entropy doesn't really. So you
suggesting it's defined to be the entropy of psi 1 through psi n divided by n. The limit.
Yeah. You can compare it with lim h of psi 1 plus psi n divided by n. Yeah, this is a.
You wanted to say h of the tuple, not sum.
But he assumed that
Oh yeah. If they're independent, then this is the sum.
Then it is the sum.
No, but if it's a tuple, I'm not. One should think more under which condition it's true. That's.
So you can't say that whenever this limit exists, the other one exists?
No, if this limit exists, then for with probability 1, this limit exists and is equal to this.
And even if
No, assuming they are not they are for 0, 1 variables or something like this. So if they are there should be some conditions for convergence. So if they are psi n is not a bit but a very long thing, then it plays too much role in the entire thing. So we need to be sure that this is kind of limit theorem can work here. But for 0, 1 variables, it's true. But what classical information theory does, usually actually, let's see on the level of statements of information theory. So there are several. I want to try to make some parallels. So there is a classical inequality, and if you want to prove it, you just use the convexity of logarithms which are there. And in algorithmic information theory, of course, it's natural to try to write something like this. The complexity of a pair xy is bounded by complexity of x plus complexity of y. But there are several things which are needed to say. First, everything is defined up to a constant, so we should add O of 1. Second, we need to say what is the complexity of a pair. So pair is not a string, so formally speaking, we need to define this complexity. And so we take some encoding of a pair. And we know that algorithmic transformation doesn't change complexity more than by constant, so it's not important which encoding we take. We have we can transform from one to another. And the last thing we need to correct, it should be not O of 1, but unfortunately it's O of logarithm of these quantities in question. So these two numbers are only logarithmically close. And this is because how you prove this? You have a program for x, you have a program for y, and you combine them into a program for pair. And still, you need something to distinguish between this, where the one ends and the other starts. So you need, for example, you need to specify the length of this program. So you need to write L in binary in advance, and encode it in some way so you can be self-delimiting and so on. So there is some overhead
but then why
here.
did you go only with the log of one of them, like the first one?
Sorry?
Why did you say that it goes with the log of the sum of both?
Oh yeah, of course you can say of this one. No, but it's so unsymmetric. Then you will ask what a stupid thing. Why it's only a log of the first one when they are symmetric? So there is a minimum. Yeah, minimum is okay. Yeah. Then it will be symmetric. But
The definition suggests that you consider only putting programs sequentially, right?
yeah.
What happens if you put them? Do you have a definition for putting them in parallel?
No, you mean executing them in parallel, or it can change only the execution time. So of course, there is, even if we want to execute the programs in parallel, we can still write the program sequentially. It doesn't really matter.
But would you have an equivalent, an analogous equality?
Okay, for example, we can write if it is P1, P2, and this is Q1, Q2, we can write P1, Q1, P2, Q2, yeah, for proving such a thing. But we cannot have a definition, because since computation time is irrelevant in this definition, we cannot take into account any issues of parallelism. It's just abstract computability. So what I should say, that this is the Kolmogorov complexity is a part of general recursion theory. So actually has some heights in 50s and 60s, and then people probably become tired of this general recursion theories, which prove something about high degrees and even higher degrees and so on. And then strangely, these recursion theories have a new place to hide. They prove now theorems about Kolmogorov complexity, but still they proved all simple theorems, and again went to these high degrees. So now there is a very nice book of Downey and Hirschfeld on computability and randomness, and there is a very advanced stuff which I never dare even to try, but still it's recursion theory. So that's what I said, and this is the. And it's a bit strange why here we have this convexity of logarithms, and here we just add the programs, append the program one to another. So why there are parallel statements, and so strangely different proofs. Both are trivial, but still. So let's look on another thing, which is conditional complexity. So here we need to define conditional complexity. And conditional complexity, as you may guess, you can actually define this as a difference, but it's not fair. So conditional complexity is measures how length of program P, which maps x to y, or y to x. So the condition is given, and you need to obtain, before we measure the program P, which produced x from nothing, and now this program is produced x not from nothing but from y. So for example, the complexity of x given x is always a constant, because there is a program which produces one program which always does this. So we can define this a natural definition, I hope you agree, and then we can ask whether there is a parallel statement, and indeed it's true, and also with the same logarithmic precision. And in one direction we have the same argument. We have two programs. First program for x, and then the second was program for y. But also as well, the program, the second will be program for y given x. Because after the first program finished, we know x, so we can supply this as an input to the second program. So we get this direction. The complexity of pair is less than complexity of x plus complexity of y given x plus logarithms. But what is the different thing? If you look, just try to prove it, it's a bit strange, because imagine you have some program for the pair. There is no reason to believe that this program is of this type, that it starts with some program for x, and then the program is transforming x to y. It may start with y, or it can produce x and y at the same time. So there is no reason to believe that every program is of this form, or can be replaced by a program of this form without loss in length.
Can I interrupt?
Yeah, yeah.
Just saying one clarification. It's really a very different. So this is really a surprising statement, because the first one is a trivial algebraic transformation, right? Basically, you can say it's just the definition of h of y.
Even it's easier than without x, because then it's even not an inequality, but just an equality.
About the h, right? So that's just h. About the
Yeah. I'm saying that compared to the inequality without x, it's even easier, because it's just an equality, not an inequality.
So
Yeah, it's indeed at first it's strange, but it's not. There is an underlying reason for this. So, okay, probably I'm out of time, so let me just try to draw something on the board. There is a combinatorial thing. So if we have a set, then we have two sets, x and y, and we have some set here. Then the first inequality with the entropy is bounded by the sum of the entropies is just that the cardinality of the set is bounded by the cardinality of its first projection and cardinality of its second projection. Oh, yeah. Log cardinality. That's so this S. And the second set with conditional entropy means that you have not the projection, but you consider the sections. So for every x, you can consider a section as yx. And then you can write maximal over x size of this section. It's smaller than the projection of entire set because it can go like this. And of course, this is only, even if we add this consider sections, it's only in the inequality. We cannot